Hello all, my name is Daphne Benderly, Senior Manager of Technology at Priestverse, and together with me today is Marie Yednak-Carpenter, Senior Applications Chemist at Priestverse, and we'd like to share with you the presentation that we gave in December 2020 at the SEC Annual Technical Scientific Meeting titled Texture Analysis and Strength Evaluation of Pressed Powders. The topics we'll be covering today is, first of all, an introduction to powder cosmetics, a little bit on the formulation framework and processing specifically for pressed powders, the test methods that we're going to be covering today, some sample results, and a summary. For an introduction, powder cosmetics have been around for a very long time. To show you how long in product positioning, Cleopatra's name is still being used. There are different types of powder cosmetics, either loose or pressed. Both of these types have similar raw materials. They give you similar texture, color development, and you can see here a long list of applications in which both loose and pressed powder cosmetics are used. Pressed powders are a more recent development than loose powders, and specifically pressed powders have been used to provide coverage, give a bronzing effect. They use a color corrector for skin, helps makeup last longer, and also diffuses fine line and wrinkles. And now Marie Yednak-Carpenter will take you through some of the materials and processing and trade-offs that are used in pressed powder cosmetics.
Pressed powder products, the formulation framework you can see below is a bunch of different ingredients, and we're going to go through each one of them. The filler is the bulk component of the formulation, which helps with compressibility and adds texture. Examples are talc, mica, and cerussite. Pigments help provide the shade, which can be titanium dioxide, iron oxides, and effect pigments. Texture additives can also help improve and prevent caking during formulations. And it's a combination of dry binders and liquid binders. The dry binders help with adhesion and compression, such as zinc stearate and polyethylene, while the liquid binders help to wet out the actual powders in a convective feel, such as esters, hydrocarbons, and silicones. Also can be added are actives and preservatives to the formulation. Some processing variables that happen in pressed powder formulations are applied pressure, pan size, pan shape, pan fill, environmental conditions, and there's some other things that may come up. Optimal conditions are formulation specific. Processing conditions can affect parameters such as drop strength, glazing, and payoff. Some also trade-offs that can happen in pressed powder formulations are such as dusting and glazing. When this occurs, they have to adjust the binder levels, which help to process the formulation much more readily. The binder levels can happen where if it's too high of a dry or a liquid, glazing can occur, which is a shiny appearance that happens with a little bit of payoff. If it's too low of the binder, dusting can occur, which builds up on the surface of the actual formulation. These defects can be seen after application on skin. Binder levels can be adjusted to help the actual product. Some additional trade-offs are processing and packaging, the shape and the size of the pan, such as if it's a square pan, the edges can help have a problem with the failure of the location of the actual product, so it doesn't work readily in the actual pan. Changing the size of the pan can help the quality, such as reducing the pan size, which reduces the glazing, or increasing the pan size, which can have a problem with not passing the drop test. Changing process parameters, applied pressure, affect quality. Increasing pressure can improve the actual drop strike performance, but can compromise the actual feel and application.
And now moving on from the type of materials that we're using and the applications of pressed powder, I want to talk a bit about the test equipment that we're using to measure pressed pan strength. You can see here the image of a texture analyzer. And texture analyzers came out of the food industry before they transitioned now over into cosmetic applications. There's a large number of attachments for various study size. You can look at cream spreadabilities, hardness of pressed powders, strength of lipsticks, combability of hair, extrusion out of tubes, for example, toothpaste, and many others. So it's a very useful tool in setting the effect of both the formulation and processing variables on product performance. Eventually, the goal is to relate results to human sensory perception. What I also show here is the standard probe kit, and I've circled in green the probe that we're using in these tests, in this test method. The evaluation methods that we used, we prepared model formulations in an osterizer blender, pressed 1-inch pans in a carbon manual press, making sure to hold constant the fill weight of 2 grams. 2 different pressures were used, with a constant dwell time. That cylindrical probe that I showed you in the previous slide, 2 millimeters, was used. The test speed was 1 millimeter per minute, and the penetration depth into the sample was 2 millimeters. Here's an example of test results. And what you can see on the x-axis is the time of the test, and on the y-axis is the force measured. And I'm showing here, first of all, 2 different kinds of curves so that you can see that there are different appearances to the test results. Some of the parameters we measure is the hardness, which is the peak of the curve. The hardness work is the area under the curve, and also the rigidity, which for this work we're defining at the hardness at 0.6 millimeters indentation. That 0.6 millimeters was chosen so that it would be below the hardness for all of the samples tested. In terms of results, I first want to go through some evaluations of commercial products. Looking then at a comparison in a very simple formulation between different grades of cerussite as a proof of concept. Moving on to comparing talc and cerussite mica as a filler. And lastly, comparing between different grades of silica as the surface, as a texture modifier. For the commercial product study, then sets were purchased to get a read on what kind of values are encountered in commercial products, and these were all chosen to be round pans of similar size to what will be used later in the experimental work. And I'll be showing you in the next slide, there's a wide range seen in measured values and also the shape of the curve, and this is useful to compare the experimental results we see to products that are already commercial in the market. So here for the numerical results, I'm showing you the minimum and maximum value for palette 1, which consisted of 16 colors, palette 2 of 6 colors. And also here you can see the curve where the softest one gave a smooth reading, and the hardest one did have that 2-peak appearance, and that's due to the appearance of a type of crust that formed and broke, and then the probe continued to penetrate into the sample. Looking at our first framework formulation, proof of concept, this is a very simple formulation. No pigments were included. Looking at 2 different kinds of mica, either cerussite SL or cerussite FSE. Dry binder varied in level. Our liquid binder is permethyl 102A and a preservative. And I first want to go through some of the differences between cerussite SL and cerussite FSE. What you can see here in the table, they're similar in particle size. They're very similar in oil absorption, but they are different in bulk density, which tells you about how well they pack under the flow of gravity. So here are the results that we saw. Again, as a reminder, the results, the comparison between SL and FSC in terms of their physical parameters. And to talk a bit about those parameters, particle size is very commonly used for powders. Bulk density is how well it flows, and the oil absorption is the amount of linseed oil required to wet out the powder. For our results, we can see that there is a very large difference in hardness and hardness work when a grade of mica is switched. It's interesting also to note that cerussite FSE, which has a lower bulk density, which means it does not flow as well when being placed into the pan, gives a lower hardness. Reducing the dry binder level, as expected, also gives lower hardness because our powder formulation is less compressed. Moving on to a second framework formulation, and here we are incorporating pigments, looking at various bulk powders, same dry powder binder. Different grades of sphere and silica are used as the texture modifier. The pigment blend is the Sympholite series. Permethyl 102A is liquid binder, and again used using the useful preservative. So breaking it down, when comparing different filler powders, mica versus talc, we can see we can easily differentiate between the talc-based and the mica-based framework. The talc gave a higher hardness, so better compression. We would need to have additional functional evaluations to evaluate performance in a fully formulated system. Looking at the change in press conditions, these are the same cerussites and talc that I showed in the previous slide, but looking at preparation at either 1200 psi or 800 psi. Not only do we see a difference between cerussite and talc, We can also see a difference between pans prepared under two different conditions. As expected, when pressing at a higher pressure, we see better compression and so higher hardness value. And it's important to remember, as Marie mentioned, that there is a trade-off there. Pressing under a higher pressure can lead to glazing. So this is an example of trade-offs between processing and performance, such as glazing versus hardness. Moving on to the third area, choice of texture modifier. Here we're looking at different silicas, and that's used at a low level. It's 5% of the formulation. And looking in at two different preparation pressures. And what's interesting to see here is that even at that low use level of 5%, the choice of our silica can affect the compressibility. That's likely due to the different oil absorption values for those different silicas. And again, we see that the processing conditions can affect the press pan parameters. And again, this is even at this low use level of 5% for the silica. So in summary, what we're showing here is a characterization test method for press powder cosmetics using a texture analyzer. It can differentiate between processing conditions, such as pressure, that 800 versus 1200 psi that I spoke about. Pan fill, I did not have time to show those results, but filling to the 2 grams, which I showed here, 1.7 grams, also did show a difference in performance. Differentiate between choice of the bulk powder, talc or cerussite, and choice of the silica texture modifier. Further work would be needed to combine these findings with consumer-relevant parameters such as appearance, payoff, color development, and sensory attributes. We would like to thank our co-workers, Joel Sabados and Maria Mo, for their contributions to this project. And thank you for your attention. Please feel free to email either Marie or me with any questions or further suggestions.